So, just so that you know, I'm Christina Krueger.
I'm Adam Hutchinson.
I'm Ellery Klein.
And we're the 3 students that have been working with the LEAFHouse and specifically the Liquid Dessicant Waterfall system over the course of the semester. So today we're going to be presenting about everything that we've accomplished throughout the semester, all the steps that we took to do what we have. And we had 2 major focuses, and the first one was repairing the Liquid Dessicant Waterfall system to like a functioning state. And then the second half was creating an energy model of the house through the system Energy Plus. And so the presentation is just going to go through those 2 aspects. And so basically the point of the Liquid Dessicant Waterfall system is to reduce the latent cooling load of the air conditioners by dehumidifying the space. So the idea is that at any given temperature, the air can only hold a certain amount of moisture. And so as you're cooling the air, you'll reach a certain point where you can no longer cool the air unless you reduce some of the moisture. And so a traditional air conditioning system will do that by condensing the air, and it's actually, it uses a lot of energy to do that. Whereas the Liquid Dessicant Waterfall system just has a few fans and then heats the water, which is a much more efficient way of removing the moisture. So the idea is to reduce all of that energy that a traditional air conditioner would use to remove the moisture. And so the Liquid Dessicant Waterfall system has 2 major parts. There's an indoor and an outdoor unit. The indoor unit is right here, and the idea is that there's fans up top which create a vacuum, and it sucks air up through the bottom and then up through the air gap where the clear part is, and then the air comes back out. And as the air is flowing up, the desiccant solution is sprayed onto the air, which absorbs the moisture from the air, so that the air coming out is dry air. And so as the solution continues to absorb more and more moisture, it loses its ability to keep absorbing moisture, so then it has to be regenerated, which is where the outdoor unit comes in. So it flows out through pipes that run under the house, and it goes into a holding tank, and then from the holding tank it goes into the regeneration chamber, which was where the solution is heated, and then it evaporates up into those 3 tubes, and then the moisture is released, and then the strong solution comes back into the house, and the cycle continues. And theoretically this cycle is a closed cycle and can continue forever. So when we originally got to the house, the desiccant system wasn't working, so we made some major modifications, and now it's functioning to the point where there's liquid running through the system and not necessarily doing what it's supposed to, but the whole system is mechanically functioning right now. So on the indoor unit, with the help of Song, we had a lot of help with Song through the whole process. He helped us replace the fans, and so one of the major complaints originally was that the fans were very loud, so when the system was on it was like annoying. But since the fans are now DC fans instead of AC fans, it's a much quieter system. And then, so you can barely hear it as opposed to before, it was very, very loud. And then we also cleaned out the holes that feed the solution into the waterfall, because they had a lot of dirt buildup inside of them, and it was preventing a lot of the holes from streaming down. And then we vacuumed out the old solution because we had no idea what was in it and how long it was sitting there. So we vacuumed that out so that we could replace it. And we actually flushed the whole system with water so that it could clean out all of the pipes. And so for the outdoor unit, the container holding all of the solution was shifted. So a lot of the PVC pipes and connections were broken and cracked. So we had to replace a lot of the PVC pipes, a lot of the connections, and 2 of the pumps and a fan, since a lot of that system was shifted. And then Song helped us add a cover to the back of the container so that debris wouldn't flow in and mix in with the solution when it was running. And then we restored water pressure to the tubes, the white tubes that come up into the evaporation tubes, because we actually found a tube that was just leaking water into nowhere, and so the pipes weren't working. And so this is a picture of some of us working on some of the indoor stuff. So Song helped us remove the whole unit from the wall so we could actually see what was behind it. And we were able to look at all the wiring, see where everything flowed out and everything flowed in. And then this is actually us vacuuming out the solution, and then we flushed it later. And so this is the outdoor unit, this is the cover that was added, and then this pipe was replaced because it was like bent all the way over here, and then this pump was replaced because it was cracked since the whole thing bent. This pump was replaced, and then this whole section of PVC piping was replaced. And we did that with primer and all-purpose cement. And then this is a picture of us flushing out the system. And so as it stands now, it mechanically functions if you want to turn it off. And then if we turn the outdoor unit on, everything flows in and out. And it's like all the mechanical pieces are functioning and liquid is flowing through the system. But obviously there's a lot more improvements that we want to make. And then we want to see if it actually works to remove the moisture. So some future improvements into the summer semester are adding the actual CaCl solution, which we have, but we want to make some more modifications before we actually put it into the system. And then we, during Maryland Day, we noticed that when the system is on for an extended period of time, like multiple hours, there's actually water buildup on the back of the wood. And we think it's from back spray, but we're not sure, so we were going to think of a solution for that, potentially like a filter. And then we want to add sensors, like humidity sensors and temperature sensors, to get live feed of the actual, like what's actually happening, and to collect some data. And then we, if you've ever seen the Watershed House, which most, I think all of you have, they have plastic orbs inside of the air gap, which helps increase the surface area of the desiccant solution trickling down. So we wanted to add those, which is both an aesthetic appeal and a functioning piece. And then as far as the outdoor unit, we wanted to create 2 separate holding containers. So right now there's a mixed solution inside one big box, and we wanted to separate those into a strong solution and a weak solution, so that the weak solution flowing out doesn't get mixed back in with the strong solution. We just think it would be a more efficient process. And then we want to install a new heat source. So originally it was designed to be heated by the solar water, which is on the roof, but there's no glycol solution within that system, and we tried to get it working, but we don't have the expertise to do that right now. So we were thinking of either building our own smaller system right by the desk, right by like the outdoor unit, or installing like an electric heater because it needs to heat to near boiling to be able to actually evaporate all the moisture. And then we want to replace the white evaporation tubes because a lot of them have cracks, so it doesn't properly release the desiccant solution. So this is just an image of the idea of like splitting the tanks up. So we have just the weak solution going out, and then it gets replaced, and then a strong solution. So originally this was 1 tank instead of 2. And basically the idea was that we did all the reparations with the Liquid Dessicant Waterfall system, and then on the entirely other level we created an Energy Plus model because we wanted to fix the system, create the energy model, and then eventually in the future combine the 2 ideas to see how the desiccant affects the energy model.
So I'm going to explain a little bit about the energy model and explain about what is Energy Plus. So Energy Plus is a program that was created by the United States Department of Energy, and it is used to for energy analysis, and it's a thermal load simulator, and it takes in various inputs such as the building geometry, the HVAC systems specs, and interior equipment, lighting, etc. And it is used also with OpenStudio and SketchUp. So SketchUp is pretty much a Google CAD software that we use to draw the LEAFHouse geometry. And you can go to the next. So yeah, this is an image of, we input a lot of the data, like the thermal properties, into the OpenStudio, and we input the geometry and the CAD drawing into SketchUp, and these things go into Energy Plus where the analysis occurs, where it takes all your data and runs it through. There's a weather file for a nearby airport in Virginia, and that it uses the weather at that location throughout the entire year to simulate how the energy usage is used within the house, how well it performs, what all these systems work. And you can go to the next slide. So yeah, this is an overview of our process for how we created the energy model. So we created the building envelope using Google SketchUp. We modeled the building materials and constructions, modeled interior lighting, electrical equipment, and modeled all the mechanical equipment, found their coefficients of performance and everything else, all the inputs that we needed for Open Studio. The air conditioning and heating, ventilation. The solar panels, we had to use a different method, which Ellery will get into later, and had to model the hot water usage. We had Eli actually helped us create a schedule because it's really important for us to know what is running at what time, what electrical equipment we're using, when the lights are on, because that will affect our outcome from the simulation. So the next slide, I think, has a picture of our CAD drawing. So this is what our drawing looks like using Energy Plus, and or using, I'm sorry, not Energy Plus, using SketchUp. And a really cool feature of this thing is we can choose a wall and go to if you can go to the next sketch, and not that one, the next one, sorry. This is a cross section of one of the walls. It's specifically this wall right here, and it has metal cladding on the outside. This drawing is from the architectural drawings for the LEAFHouse, and so we can input all the information that we get from this, which is, there's corrugated steel metal here, corrugated steel siding here, and then it goes through all the other materials, the house wrap, the studs and the insulation, and the spray foam insulation, and the gypsum board. And each one of those materials has their own thermal properties, and they have a corresponding resistance, corresponding conductance, and corresponding specific heats that affect how the energy model will run. So what I needed to do was go through and find all the material properties, and I tried to use the BCL, which is, can you go back one slide? Yep. Thank you. The BCL, which is the Building Component Library. I tried to use ASHRAE as much as possible because they were, more reliable sources, and there's also an Energy Plus database for analyzing the properties of the windows and the doors, and anything that I couldn't find within there, I had to look up online and find on thermal property tables. So can you go forward 2 slides? Yep. This is an example of that wall right here. So I have, the thickness, which is the total resistance is rho L over A, which is L is pretty much your thickness, and A is the area of the wall, which is given to us using the Google SketchUp. So all these things, all these different materials, the resistance is sort of like added up from each one of these to create an equivalent resistance of the wall, and that's how Energy Plus simulates the data, simulates all of our inputs. And I just wanted to make sure I was doing everything correctly, so I used multiple units. I have conductivity in SI units and in American units, just to make sure I didn't make any mistakes anywhere, make sure everything worked out right, and the units checked out. And one thing that was sort of difficult for us was the corrugated metal cladding had to be modeled as an partial air gap and then partial without an air gap, so we created just an equivalent resistance of that thing. That's why it's not listed here, because we just created our own equivalent resistance. And yeah, that's it. Okay.
Alright, so one important aspect to energy modeling is modeling all the interior equipment that uses electricity. So what does this include? It includes things such as computers, laptops, microwaves, printers, basically anything that uses electricity in the house we had to model. So what we did was we had to go through manuals within the house, we had to go find online manuals, we had to find the power usage of all these appliances. And if sometimes we were unable to find, if the house didn't have a manual itself, and there was no online manual. We had to actually calculate it using some basic physics equations such as power equals IV. And so once we had the power of every appliance, we would apply schedules based on the schedules that Eli provided us. And so over the course of the year, the energy model would calculate, the schedules would tell when the appliances are on or off, and so when they're on, it would run them, and that would add the electricity consumption to the house, and then at the end of the year, in the report, it'll tell us how much energy all the appliances use in total. So very similar to electrical equipment is the interior lighting. So the LEAFHouse has two main lighting groups that are in use. There are actually 4 or 5, but only 2 get used. And that's that they're all off, and that there's the low lighting group. So the low lighting group uses a total of 211 watts. So similar to the electrical equipment, we apply a schedule, and over the course of the year, this schedule calculates when the lighting is on or off, and at the end, it'll add all the consumption up and add it to the total power consumption of the house. Some other inputs that we needed to find for lighting was the fraction radiant and fraction visible. So fraction radiant is the amount of thermal energy that from the lighting that gets transferred into the walls of the house, and then fraction visible is the amount of thermal energy that gets released directly into the space. All right, so probably one of the more challenging and more important aspects of energy modeling is heating and cooling. That is normally the largest load of any building. So this building uses a Friedrich mini-split ductless unit, and it's just a basic HVAC heat pump and air conditioning. In the summer, it acts as an air conditioner, and in the winter, it acts as a heat pump based on the flow of the refrigerant. So here's a basic diagram of the mini-split system. So depending on if it's heating or cooling, the refrigerant will flow in different directions. So this is basically all this is outside in the outdoor unit, and these are the 2 units you see right there and in the back of the room. So depending on which way the refrigerant is flowing, it'll either be heating or cooling the house, acting as a heat pump or an air conditioner. And so within Open Studio, they actually have a variable refrigerant flow option where you can add the outdoor unit and the indoor units, and the indoor units are connected to the thermal zone, in which this case it's the main room. And so if you click on each of these, it comes up with a bunch of inputs. So we had to put in all these inputs, and these include the cooling capacities, heating capacities. We had to calculate coefficient of performances, sensible heat ratios, and sometimes things we could not calculate. We had to find some, we had to assume some values that are some general common values for a system like this. And so here's an actual output from Energy Plus showing the simulated temperatures during spring 2014. So this is actually between May 2nd and May 8th, so right around this time. So we had the set point temperatures between 68 and 78 degrees Fahrenheit. So the goal of the air conditioning system is to keep the temperature within this range. So as you can see, during the day, the temperature will rise. It will hit the threshold, and the AC will turn on, and it will keep the temperature from going above that limit. And then when the temperature cools down, it will cool back down. So this is good. So it shows that the energy model is, the AC system in the energy model is functioning properly. It's turning on and off when it should, and regulating the temperatures. Now this is during spring, so temperatures aren't too hot or too cold outside, so it isn't too much of a, it doesn't give the AC too hard of a time to regulate the temperature. Another important aspect is the air ventilation. So this house has an energy recovery ventilation system. So it has an air-to-air heat exchange. So basically when incoming air comes in, it exchanges heat with the outgoing air. And so say it's really cold outside and it's a comfortable 75 degrees indoors, then the heat exchange will heat up the incoming air so that when it finally gets dumped into the house, it's at a comfortable temperature. Now this also reduces the load on the air conditioning system, so it doesn't have to work as hard. So it's an important energy saving appliance of this house that we modeled. So you can see there's the air-to-air heat exchange, a fan that circulates the air, and here's the actual zone that we're sitting in right now. And so yeah, as Adam mentioned, there is not an easy way to model solar panels, interestingly, in Open Studio. There is an Energy Plus, but not the Open Studio graphical user interface. So what we used the National Renewable Energy Laboratory. They had a program called PV Watts, and this took into account a weather file, which is the exact same weather file we use for Energy Plus. We gave it some inputs such as the amount of snowfall per year, so that days that snowfall is like there's no capacity. The weather file would take into account for when there's clouds, when there's not as much sun, and also we calculated the total capacity of the solar panels based on the manual in the house. So if we gave the program all these inputs, using the weather file, it generated a rough estimate of how much energy the solar panels produce, and we estimated about 9,800 kilowatt hours per year, which is a good amount. All right, and one of the last things to model is the hot water usage. So the LEAFHouse doesn't use much hot water. Really, only 3 things using hot water are the dishwasher and the 2 sinks. The shower is not currently in use, so we didn't need to model that. So it uses a tankless hot water heater, and on the setting, it heats the water to 42 degrees Celsius in the tank. And so here we have the actual hot water heater, a pump that circulates the water, a temperature set point, and the actual output. So this would include the sinks and the dishwasher. So you would click each of these things and it would pop up with more outputs for us to input data about those. Oh, and we've been talking about schedules. So here's an actual schedule. So here's Eli's occupancy schedule. So this is for on a Monday. So he wasn't here between midnight and around 10 a.m. and then he was in the house between 10 and about 6 o'clock and then leaves. So we applied schedules for basically every appliance, for the AC system, for occupancy. Basically, you need schedules for everything because it determines how much things are being used, which is very important for energy modeling. And so each day of the week has a different schedule based on usage. So this is a very important process for us because it's very detrimental, because if we have a schedule that say it's always on, then they'll have a much larger energy consumption than say if it's only for a fraction of the day. All right, so here's some actual results from the Energy Plus model. The red is the heating, the yellow is the interior lighting, black is the interior equipment, the pink is the fan, so that includes the fans with the AC in it, and then the orange is the water systems. So as you can see, the heating and cooling make up a large portion of the energy consumption. And originally the house wasn't planned to use these systems. So if these systems were not here and more of the systems inside the house were functioning, such as the radiant flooring, then energy consumption would be drastically reduced. And so here's the energy consumption compared to the solar panel production. As you can see, the house produces about 88% of its own energy based on our simulation. Now this is most of its own energy. And again, this is a simulation, so these readings would need to be verified, but we generally think that these are accurate. And again, the system was not initially meant to have the system, which uses most of the energy. And so here is the temperatures within the house over the course of the year. And so we have the set point in between 78 and 68 degrees Fahrenheit. And so as you can see in the spring and the fall, the AC system is able to control the temperature and keep it within a comfortable range. However, during the summer and the winter, it has a hard time, and the temperatures tend to get increase and decrease in their respective seasons. So based on our simulation, we believe that the AC system is not fully sized for this to heat and cool this house. We believe that maybe during the competition when it was modeled in October that it wasn't modeled specifically for the hot summers and the cold winters, and that the radiant flooring and the solar hot water heater are also not functioning currently. Were meant to be used to help heat and cool the house. And also, we did not model the liquid dessicant waterfall, which also was supposed to help reduce the load on the AC system. And it is circulating, but it's not functioning currently, so we didn't include it in our model. So these are some reasons why the temperatures in the house are not regulated very well. So conclusions. The house generates almost all of its own electricity, even though it wasn't designed to initially have these two AC units, which is pretty awesome. Has 88% of its own energy, and heating and cooling make up most of its own electricity. We modeled the mini split system as always on. Now, if the AC heating units were instead scheduled to have setbacks, so say at night, maybe they're set off and then a couple hours before people come in, they're turned on, then this would drastically reduce energy consumption. However, this would also vary the temperature more, so it might not have enough heating or cooling capacity to cool it or heat it to a comfortable temperature before people enter the house. And again, some reasons why the temperature might not be controlled very well is that the breathing flooring is not functioning, that the solar thermal water heater is not functioning, and the liquid dessicant waterfall was also not modeled. So these are some reasons why the temperature may not be regulated, or is not regulated very well in our simulation.
Okay, so far we've just talked about mainly like the reparations we did to the Dessicant waterfall system and all of the energy modeling that we worked with. But like, why should AIA care, and like, why is AIA helping fund this project? And the main idea is to get a better understanding of the energy consumption of the house as a whole. And sustainability is huge in the field of architecture right now, and so we have all these sustainable features on this house, but how are they actually contributing to the overall energy consumption? And I mean, the house is advertised as net zero, so the idea is to create like an educational, promotional platform. And currently we have the theoretical models, and we have the Dessicant system, which is sort of a separate project. And the idea, we hope to, like in the summer semester, actually get actual data and collect actual live feed about how the house is functioning, and then we hope to display those somewhere within the house, so you can have a constant sensor system and like constant live feedback about what's happening. And then you can potentially bring in architects and people from the public and students, and you can use it as an educational piece to show like different features and how everything's working together. And it's very like promotional, promoting sustainability and like promoting everything that the house stands for. So that's what we're hoping to give back to you.
So during future semesters for the Liquid Dessicant Waterfalls course, we hope to, like Christina said, collect data, real live data for temperature and humidity, and we plan on putting some sensors at the input and at the output of the system to tell exactly how well the system performs, and maybe set up some sensors throughout the house, and just find out, you know, how the moisture in different locations throughout the house, how that changes with time. And other projects we would be working on in the next course would be modeling the liquid dessicant system in engineering equation solver, EES. They have energy equation solver is a program used to model a lot of thermodynamic systems, and it has the properties listed within it, all the properties that you would need, the enthalpy tables and steam tables, everything that you would need to model thermodynamic processes. And we would continue to add new modifications of the LDW system. So that's what we hope to do in future semesters, or in the next future semester over the summer. And we acquired, one thing that we're really grateful for is the opportunity to get real life experience using a lot of the principles we've learned in our classes, the thermodynamic classes, basic heat transfer concepts, load calculations, how the liquid dessicant system works, using Google SketchUp, energy modeling process, and analysis of the energy simulations data, because it's one thing to learn it in the classroom and be able to answer problems, answer test problems and homework problems and that sort of thing, but it's a completely different thing to try to apply those concepts in real life, and how you would actually go about solving or finding data in a real situation, in modeling the energy of an actual house. It's a lot different. So we're really grateful for the experience to be able to model this the LEAFHouse and get information and data and that sort of thing. So we also want to thank everyone from AIA who was involved, especially Renee and Eli. Thank you for allowing us to come in here and do our research. And we want to thank Optimized Thermal Systems, Kara, and Song for all your efforts and support within this course. And we also want to thank Dr. Ling and Dr. Radermacher from the Center of Environmental Engineering, Energy Engineering. And that's all. So if you guys have any questions or